Welcome to section 1.7 Introduction to Proofs, Math 160, Discrete Methods at Anderson University. This is Dr. Gilbert Eyabi. Learning objectives for section 1.7, number 1, mathematical proofs, forms of theorems, direct proofs. We would pause there for the first part of section 1.7, and then we would return for the second part and look at indirect proofs, where we would study contrapositive and contradiction. So let's go ahead and start with mathematical proofs. Proofs of mathematical statements. Number 1, we say that a proof is a valid argument that establishes the truth of a statement. So we need to establish the truth of a statement. It is not just an act of faith. And we use a proof to establish the truth of a statement. In mathematics, in computer science, and in many other disciplines, informal proofs, which are generally shorter, are used. And those kinds of proofs have a few things in common. Number 1, more than one rule of inference are often used in a step. Steps may be skipped. The rules of inference used are not explicitly stated. It's easier to understand and to explain to people, but it is also easier to introduce errors. Therefore, it becomes very necessary that we introduce rigorous mathematical proofs. Proofs have many practical applications. Number 1, verification that computer programs are correct, establishing that operating systems are secure, enabling programs to make inferences in artificial intelligence, and showing that system specifications are consistent. So the concept of proofs is very important, not just in mathematics as a subject, but also in practical applications. Let's look at a few definitions. Number 1, a theorem. A theorem is a statement that can be shown to be true. So a statement that can be shown to be true is known as a theorem. If it is not yet shown to be true, it's a conjecture, and we will look at that later. What do we use in showing that the theorem is true? Well, we use definitions, we use other theorems, we use axioms, we use rules of inference, we use something we call lemma, at times proposition. So we will see this later, but this is exactly what happens if I'm proving directly, or what is known as direct proof. I want to prove that P implies Q. I suppose that P is true, and I have to prove that Q is true. RTP means required to prove. So I start off with proof. Suppose P is true, required to prove Q. Then I proceed and say, but P true, what does that mean? Implies. Then I use definitions, I use theorems, I use rules of inference, I use axioms, I use lemmas, I use propositions. Whatever it is that I need to use, I put all of those together to prove that P implies Q. And when I'm done, we use this little nice square, which is known as a tombstone. It means done. The problem is finished. Or we can say, I killed the problem, or I nailed the problem. You might see others use QED, which means proved beyond all reasonable doubt, and at times something a little bit less dramatic. Okay, what is a lemma? A lemma is a helping theorem or a result which is needed to prove a theorem. So that's why I've included lemma right here, because it is usually used when proving a theorem. What about a corollary? A corollary is a result which follows directly from a theorem. Very often it's a generalization of that theorem. For example, if I can prove that something holds for A intersection B, then I can come up with a corollary that shows that if I have sets A1, A2, A3 up to AN, then that same property holds for A1 intersection A2 intersection A3 intersection AN. So that is a corollary. It's a generalization of the theorem. It follows directly. At times, you don't need any proof because it follows directly from the theorem. Now, some less important theorems are called propositions. If you read many books, you would see theorems, you see lemmas, and then you see propositions. And then we have a conjecture. A conjecture is a statement that is being proposed to be true, but we have to prove it. For example, Alice has never seen her father cry. Alice has never seen her husband cry. And then she stands up and makes a conjecture. Men do not cry. That's not a theorem. That's a conjecture. It needs to be proved. Of course, if we can come up with an example of a man who cries, then the conjecture is destroyed. It never becomes a theorem. But if we can prove that for every X, where the domain is a set of all people in the world, if X is a man, then X does not cry, then that conjecture becomes a theorem. And of course, that particular conjecture is false. Okay, let's move on. Let's look at some forms of theorems. Many theorems assert that a property holds for all elements in the domain, universal. Remember universal quantifier? So the theorem asserts that there is a certain property which holds for every element in the domain. And very often the domain would be the set of real numbers. At times it could be the set of integers or some of the discrete structures that we would study in this class. This is discrete methods, discrete math. So often the universal quantifier is omitted by standard mathematical convention. So for example, the statement, if X is greater than Y, where X and Y are positive real numbers, then X squared is greater than Y squared. You see here that we do not use the universal quantifier, but as a matter of fact, it's there somewhere. If you rewrite this statement, it would be, for all positive real numbers X and Y, if X is greater than Y, then X squared is greater than Y squared. Now you see the universal quantifier in place. So if I simply say that if X is greater than Y, then X plus 2 is greater than Y plus 2. What I'm actually saying is that that holds for every XY. And if my domain is a set of real numbers, then there is a problem because it may not be true, since I have positive and negative numbers included in the show. If I'm dealing with positive numbers only or negative numbers, what do you think? So we need to know what the domain is. And we also need to know whether the statement needs a universal quantifier or, guess what, an existential quantifier. For a universal quantifier, as we mentioned when we were dealing with rules of inference, we just cannot use an example to prove that a universal quantifier is true. We have to show that it is true for every element in the domain. How do we do that? Well, that's why we're dealing with proofs. Let's move on. Proving theorems. As mentioned before, many theorems have the form for every X in the domain, P of X implies Q of X, universal quantifier. To prove them, we show that where C is an arbitrary element of the domain, P of C implies Q of C. Now, recall this. Now, note very carefully that we are not using an example to prove a universal quantifier. We are saying that we chose C arbitrarily or at random from the domain and then prove that P of C implies Q of C. Once that is established, then we can use our universal generalization to conclude that for every X, P of X implies Q of X. So, whatever happens, we must prove something of the form P implies Q. So, this is what I just mentioned. This is different from using an example to prove a universal quantifier. You cannot use an example to prove for every X, P of X. You prove it by using universal generalization. You show that if C is an arbitrary element in the domain, then P of C is true. If that happens, then you can claim that for every X, P of X implies Q of X is true. On the other hand, when we look at existential quantifier, all you have to do to prove an existential quantifier is to provide an example. But right now we are dealing with universal quantifier, and you can only do that using the idea of universal generalization. Let's look at a couple of proofs. Number one, trivial proofs, and number two, vacuous proofs, and then we would look at what is known as direct proofs. And in all of these, we are proving the conditional statement P implies Q. So what are trivial proofs? If we know that Q is true, then P implies Q is true as well. So there is nothing to prove. Recall, F implies T, is true. True implies true is true. In both cases, Q is true. So it doesn't matter what P is. As long as Q is true, P implies Q would be true. So false implies true is true. True implies true is true. So these are called trivial proofs. For example, if it is raining, then 1 equals 1. We know that 1 equals 1. So whether it's raining or not, if I ask you to prove that, all you do is proof. The proof is trivial. End of proof. Or you simply say trivial proof. End of proof. Period. Or if you want to elaborate some more, you can say, since 1 equals 1, we can conclude that if it is raining, then 1 equals 1 using a trivial proof. End of proof. That's all. That is how you prove any statement where Q is already known to be true. We call that a trivial proof. The next is known as a vacuous proof. If we know that P is false, then P implies Q will be true. Look at this. These are the 4 possible options. So if P is false, false implies true is true. False implies false is true. Recall that the only time where implication P implies Q is false is when we have true implies false. So if P is false, it doesn't matter what Q is, it would always be true. For example, so if I ask you to prove the following statement, prove that if I am both rich and poor, then 2 plus 2 equals 5. We proceed as follows. Proof. Since it is impossible to be both rich and poor, we conclude using a vacuous proof that if I am both rich and poor, then 2 plus 2 equals 5 is true. End of proof. We're done. Or you could just say proved vacuously. And any mathematician would understand that your P is false. And therefore, it doesn't matter what your Q is. Vacuously, the proof is done. Okay? So we have trivial proofs and we have vacuous proofs. Now, I should mention that though these examples seem really silly, both trivial and vacuous proofs are often used in mathematical induction. And we would see mathematical induction not only in chapter 5 of this class, but we shall see it again in abstract algebra, and we shall see it again in advanced calculus. So do not forget the idea of vacuous and trivial proofs. Now let's move on to something even more exciting, direct proofs. Before we hit direct proofs, we need a few definitions. Number 1, what is an even number? What is an odd number? As we move forward, we will define what a prime number is, what a rational number is. But for right now, let's concentrate on even and odd numbers. We need a formal definition of an even number, and we need a formal definition of an odd number. So right here, an integer is even if there exists another integer k such that n equals 2 times k. So a number is said to be even if there exists an integer such that n equals 2 times k. This integer could even be 0, it could be positive, it could be negative. But the only way we can conclude that a number is even is if there exists an integer k such that n equals 2k. What about odd? A number n is said to be odd if there exists an integer k such that n equals 2k plus 1 or n equals 2k minus 1. Both will be accepted. Both are definitions of a number being odd. For example, 10 is even. Why is 10 an even number? 10 is an even number because there exists an integer called 5 such that 10 equals 2 times 5. Here our k is 5. Why is 19 odd? 19 is odd because there exists an integer called 9 such that 19 equals 2 times 9 plus 1. Or we could say there exists an integer 10 such that 19 equals 2 times 10 minus 1. Okay, so you have to remember this. Whenever you hear the word even, then know that that number can be written in the form 2 times k. K is just some integer. You could call it p, you could call it q, you could call it k wiggle, but it is 2 times some integer. And if you hear that it is odd, then n is 2 times some integer plus 1 or 2 times some integer minus 1. Now, let me also mention that every integer is either even or odd, and there is absolutely no integer that is both even and odd at the same time. If that happens, math will no longer exist. That's very important. It's a very small basic fact, but we shall use it in the examples that will follow. We will learn some more about integers in subsequent chapters, but I need you to remember the definition of a number being odd and a number being even. And in a few lectures, we would then inform you that integers are not only divided as even and odd, they could be divided in so many ways. As a matter of fact, infinitely many ways. But for now, let's concentrate on even and odd numbers. Okay, direct proofs. What are direct proofs? That's exactly what I started off with when we first looked at the definition of a proof. You assume that P is true, or you can say suppose P is true. You use rules of inference, axioms, lemmas, propositions, definitions, and ultimately you show that Q must also be true. That is called a direct proof. You start off with P and you prove Q. If that happens, you would have proven that P implies Q. We will look at indirect proofs later. So let's go ahead and enjoy some very exciting direct proofs. Number one, prove or disprove. That's kind of how questions will be said in this class, so get used to it. Prove or disprove. If n is an odd integer, then n squared is odd. Let's look at the proof. I have decided to rewrite the question and the proof in the format I would expect you to remember and to present your proofs in class. So prove or disprove. If n is an integer and n is odd, then n squared is odd. And do that using a direct proof. Let's start. You say let n be an integer. Suppose n is odd. What have we done? We have assumed P. Now we're going to use definitions, theorems, axioms, lemmas, propositions, rules of inference, whatever is available to us to prove that n squared is odd. Okay? So this is the format I need you to follow when executing proofs in this class. Let n be an integer. Suppose n is odd. Required to prove RTP n squared is odd. It's always important to write this down. If you do not know where you're going, you wouldn't know when you get there. So required to prove n squared is odd, i.e. what do I really want to prove? I want to prove that there exists an integer k such that n squared equals 2k plus 1. That's where I'm going. Okay, so I put a period. Now I go back and start with the word but. What does P actually mean? What does it mean when we say P is true, when we say n is odd? What does it actually mean? Definitions. Mathematicians swear by definitions. If you hear that a mathematician is swearing somewhere, the guy is just quoting definitions and standing on definitions. Mathematicians swear by definitions. So, but n odd, what does that mean? It means that there exists some integer k1, and this k1 is introduced so that you don't always use k. It's not necessarily the same k. So there exists some integer k1 such that n equals 2k1 plus 1. That is what it means for n to be odd. So this is by definition. So n squared equals, so this is what n is. I just have to take the square of this. So n squared equals, I square all of that, and that gives me 4k1 squared plus 4k1 plus 1, which equals 2 into all of this plus 1. Remember, I am looking for some integer k, which I could call anything, but it has to be an integer, such that n squared can be written as 2 times that integer plus 1. Wait a minute, it looks like I've written this as 2 times something plus 1. If I can only prove that this something is an integer, then I'm done. So I make a huge, bold claim. I say this equals 2 times k wiggle plus 1, where k wiggle is 2k1 squared plus 2k1. Now, you cannot stop here because the goal was not just for you to set this portion equals some k wiggle. The goal was to show that this is actually an integer. So, why is this an integer? You see, I put here element in z. Now, I'm not going to expect you to write each time why it is an integer, but I need you to say where k wiggle equals 2k1 squared plus 2k1 element in z, and I hope And I expect that you understand that the reason why this is in Z is because K1 is from Z. The product of two integers is an integer, therefore K1 squared is an integer. K1 squared an integer, 2 an integer. The product of two integers an integer means that 2 times K1 squared is an integer. 2 is an integer, K1 is an integer. The product of two integers is an integer, therefore 2 times K1 is an integer. This component is an integer. This component is an integer. The sum of two integers is an integer. Therefore, I can conclude that K wiggle as defined is an integer. Again, I do not expect you to write all of that out, but I need you to say element in Z, and you need to know why it is an element in Z. So what have I effectively done? Effectively, I have shown that if n is odd, then n squared can be written as 2 times some integer called K wiggle plus 1. And that means n squared is odd by definition of an odd number. My proof is done. Tombstone. I nailed it. Let's try another example. Example 2. Prove that if n is an integer, m is an integer, n odd, m even, then 3 times mn plus 6 is even. It doesn't matter how complex these proofs may sound, just use definitions, lemmas, axioms, and before you know it, it's done. So let's try that. Let m and n be integers, so you just repeat this. Then you say, suppose n is odd and m is even. What did we do? Suppose p, we assume that p is true. Required to prove q. 3mn plus 6 is even, i.e. what does that mean? It means there exists an integer k such that 3mn plus 6 equals 2k. So this is where we're going. We put a period. Now we go back and start. But what does it mean for n to be odd? What does it mean for m to be even? N odd implies by definition that there exists an integer k1 such that n equals 2k1 plus 1. Take a deep breath. Call that equation 1. M even, what does that mean? There exists an integer k2 such that m equals 2k2. Call that equation 2. Remember where you're going. We want to prove that 3 times m times n plus 6 equals 2 times some integer. So now we can hit the nail on 3mn plus 6. So what is 3mn plus 6? 3mn plus 6 equals 3 times mn plus 6. 2k1 plus 1 and 2k2, all of that plus 6. I'm using my definitions, 1 and 2 right here, these equations. So that equals, I have 3 times, I open this up, that is 4 times k1, k2 plus 2k2 plus 6. Open that up again, I have 12 k1, k2 plus 6k2 plus 6. Where am I going again? I want to prove that 3mn plus 6 equals 2 times k. So I factorize out 2 from these terms right here, and that gives me 2 parentheses 6k1 k2 plus 3k2 plus 3. Wait a minute. It looks like I now have 2 times something. Is this something an integer? If it is an integer, then I'm done. Why is that very important? Because you could arrive at 2 times something which is not an integer. If that is the case, then it doesn't work. We shall see that when we look at proofs by contradiction and contrapositive. So we have 2 times, and I call that k wiggle, where k wiggle is 6k1 k2 plus 3k2 plus 3, and I claim that that is an integer. Again, why is it an integer? Because the product of 2 integers is an integer, the sum of 2 integers is an integer, so all of these together is an integer. What have I done effectively? I just proved that if n is odd and m is even, then 3mn plus 6 can be written as 2 times some integer k, i.e. 3mn plus 6 is even. Therefore, 3mn plus 6 is even. Tombstone, done. Beautiful. Now look at these little guys here. Prove or disprove. If m and n are integers, where m is even and n is odd, is it true that 5m squared n squared plus 7 is odd? It's a good question. In other words, can I find an integer k such that 5m squared n squared plus 7 can be written as 2 times k plus 1? What about number 4? Prove or disprove. If m is an integer and m is odd, then m cubed plus 11 is odd. I'm going to leave 3 and 4 as simple exercises for serious students, and I would expect you to include the proofs of 3 and 4 on your content summary after you watch the video. And I'll need you to present that to me in class when you submit your content summaries. And of course, if you're watching this on YouTube and you're not in my class, you could also attempt the proof and write the proof on the comment section, and that'll be wonderful. Or you can show it to your teacher or to your friend, and you guys can discuss the proofs. Math is beautiful. Before we take a break, why don't we look at rational numbers? A real number R is said to be rational if there exist integers P and Q where Q is different from 0, because if Q equals 0, we have a problem. We would be dividing by 0, such that R equals P divided by Q. So R is said to be a rational number if I can write R as P over Q, where both P and Q are integers and Q specifically is different from 0. Prove or disprove. The sum of two rational numbers is rational. In other words, if R and S are rational numbers, would R plus S be rational? That is the question. Proof. I'm going to go through mine instead of what your textbook has. This is also beautiful, but I want you to follow this procedure like I mentioned before. The set of rational numbers is denoted by Q. So we say that X is a rational number if there exists P and Q, both integers, Q different from 0, such that X equals P divided by Q. And if an element is not a rational number, then it is an irrational number. And the most famous irrational number, of course, is my favorite number, pi. We'll talk about that later. Okay, let's go back to our proof. Let X and Y be rational numbers. Required to prove X plus Y is a rational number. Okay, the sequence. Then I go back. But what does it mean for X to be a rational number? What does it mean for Y to be a rational number? But X being a rational number implies that there exists P and Q, both integers, Q different from 0, such that X equals P divided by Q. Also, Y, a rational number, means there exist integers U and T. T different from 0 such that Y equals U divided by T. Now I go ahead and compute X plus Y, which would be P divided by Q plus U divided by T, and I use my simple rules of addition of fractions, just like it's done here, and I arrive at a conclusion. And I have to prove that the numerator is an integer, and the denominator is an integer, and the denominator is different from 0. In other words, X plus Y equals P wiggle divided by some Q wiggle, where P wiggle is an integer, Q wiggle is an integer, and Q wiggle is different from 0. If that is the case, then I conclude that X plus Y is a rational number, and that ends my proof. So I would need you to polish this up and also include it on your content summary. So for this particular lecture, you have 3 things to include in your content summary. The first 2 proofs we looked about, and a nicely written proof for X and Y rational implies X plus Y rational. And I should just quickly mention that a set of rational numbers union the set of irrational numbers would give you the entire set of real numbers. That is a lot, so I think I'm going to pause right here, take a break, and call this section 1.7 part 1. Then we shall come back and look at part 2, where we start discussing contrapositions and contradictions. That would be very interesting and exciting. Thank you very much. God bless you, and I look forward to seeing you again in section 1.7 part 2. Thank you.